Hello and welcome to the 33rd and the last lecture in 19th chapter in our comprehensive course on AI, ML and DS. Now, in this lecture, we want to continue our discussion. Actually, we were doing practical applications of central limit theorem. We did first application, that how central limit theorem helps in confidence interval construction. Then second application, how central limit theorem helps in hypothesis testing. But this was a very lengthy discussion. So this hypothesis testing is the heart of data science, and therefore we continued the discussion of hypothesis testing for so long that many of you might have actually forgotten that what we are doing is actually 5 applications of central limit theorem. So it continued, this hypothesis testing discussion continued for around 6 or 8 lectures. Okay, so now we are coming back to our track, and third, quality control in manufacturing. Now these are very easy and simple discussions, and not even boring also or something like that. So we will be able to easily cover all 3 remaining applications. One, quality control in manufacturing. Second, data sampling in surveys. And third, algorithm performance evaluation. So let us first take quality control in manufacturing. Let us say you are a factory who is building metallic rods, meter rods, that is 100 centimeters should be the length, and they are not rods for some very precise or scientific kind of applications, so that very accurate measurements are required, but they should be fairly accurate, right? And you want to ensure that the rod length stays within acceptable limits. Now, suppose you are a big supplier of metal rods, and therefore you are producing, say, 10,000 rods or 1 million, 1 lakh rods, maybe 0.1 million rods per month. Now the question is, will you measure the length of each and every rod to decide that they are within some acceptable limits which you have decided? So no, we don't do that way, because that whole 0.1 million rod, that becomes my population. But we try to find one sample from that population, and we find the mean length from that sample. And if mean length comes out to be within acceptable limit, then I would say that I can confidently state that my population's mean length will also match with my sample's mean length, because central limit theorem guarantees that, provided I follow all assumptions of central limit theorem while my sampling process. So I would take random samples of rod which are independent of each other, no way linked with each other, and I will measure their lengths. Then I will calculate the standard, sample mean and sample standard deviation, and then I will use some control charts to monitor the entire process. Control charts means what? That we will see when we plot up that particular graph. So suppose you have decided that upper control limit is the mean of sample plus 3 times this standard error, this sigma divided by root n, that is called standard error. So you are allowing bigger error here, because as I said, you don't want some precision manufacturing. Bit of here and there is fine. So 3 times sigma divided by root n, or lower control error is mu minus 3 times sigma divided by root n, right? So this is upper control limit, UCL, and similarly this is lower control limit. Now let us try to simulate the process. Simulate means that as if you have to imagine that you are standing in the factory and you are actually doing the experiment. So these are importing the standard libraries, and you have decided that the true length should be 100 centimeter. So that means entire population of that 0.1 million rod which you are producing per month, that should have length of 100 centimeter on an average. Okay, so that is your true mean, should be 100. Now, how much standard deviation you want to allow? Then 2 units, or that means say maximum 102, minimum 98. Not more than that allowance you want to give. Sample size is 10 and number of batches is 50. So what you are doing is that you are from those 0.1 million, you are taking a sample of 10 rods, but that only 10 rods, then that will violate the condition for central limit theorem, right? Because greater than 30, then only normality can be guaranteed. So you can say that I would take 10 rods, but I will not take only one sample. I will take 50 such batches, each of 10 rods. Okay, so that means from those 0.1 million, one batch will be selected from here, one batch will be selected from here, one batch will be selected from here. That is how sampling is done. I have shown that process many times. So population and sample process. So you are knowing that how we do it. This is how we do it, right? Just a minute. Yes, this is how we do it. So these are, suppose, those 0.1 million rods, okay, from which I have taken 50 batches. Each colored bubble, small bubble, is a batch, and in each batch there are 10 rods. So you take such 50 batches and find the length of those 10 rods. Okay, so you are doing that kind of sampling. So suppose you have taken sample size of 10 and 50 such batches. So now you are not violating the central limit theorem condition, that your total how many observations you are taking, then for 50 multiplied by 10, or 500 observations. Okay, now let us simulate the data for those samples. Here I am simulating, but there you will select those 50 batches of 10 rods each and separate out. That will become your sample, 500 rods, and then you will measure their length and put them in a list. But here I want to simulate the data. So first I simulate the data itself like this, np.random.normal true length. So that is my 100, and standard deviation, that is my mean which I am targeting. So 100 centimeter mean, 2 standard deviation 2 centimeter, and sample size of 10. And then how many such batches you have to take? Then for underscore is means for I in or n in, anything you can put in range num batches, right? So how many? 50. So 50 such batches you will take. You will find the of 10 units each, such that in each batch the mean value is 100 and the standard deviation is 2, and you will measure the length. So as I said, this is the data. So we are simulating it because we don't have access to a physical factory. So we are trying to simulate the data. And then let us print the data, and let us print the batch means both. Okay. So if I print the data, these are those data points, 10 in one sample, and you can see that length of 100.99, length of 1 is even going 103 also. But that is one rare case, right? And similarly, this is also going 103 also. But that is because I am considering only one sample. So that does not give idea about my sample completely. Forget about the population. Forget about this whole population. It does not even give idea about my sample, because my sample consists of 50 such batches of 10. Okay, so this is just one batch. So I will find the mean of this one batch, and the mean of that first batch suppose comes out to be this much. Then I will take another batch, second batch. It will also have such 10 observations, from which I will find the mean of that second batch. Suppose that mean comes out to be this much. Then I will take third batch. It will also have some 10 observations like this. I will find the mean of that. That is the mean like this. And similarly, I will take 50th batch finally. And these are the mean values for the 50th, the 10 rods of that. And this is the mean, not mean values. These are the values of lengths of 10 rods. And this is the mean value for that sample, 50th sample, right? So then these are the batch means. But batch means is also not the final, because what is the sample mean? So sample mean is the mean of all this I have found that are batch means. These are suppose those 50 batches. But now I have to find the mean of all those means. That would become my sample means. So that is done here in the next step. Mean length is equal to np.mean batch means, right? And then you find standard error. So the standard error is sigma divided by root n, or that is standard deviation this much divided by root n. That is my standard error. Then you select the upper control limit. How much you want to allow? You want to allow on the higher side mu plus 3 multiplied by sigma divided by root n, and on the lower side mu minus 3 multiplied by sigma divided by root n. So you allow upper control limit and lower control limit, and print mean length, standard error, upper control limit, lower control limit. So if you do that, then now you find the sample mean to be 99.99 centimeters. So you see that even if 1 or 2 rods are like this, if you have taken a sample of 10, and if you randomly select 10 rods and you randomly select 50 batches from your population, then finally find mean of each batch means, and then find the mean of all batch means. That will become my sample mean, and that came out to be 99.99 centimeter, which is very close to what I was aiming for. True mean should have been, so true length should have been 100. So that is the targeted mean, targeted length or population mean. So my sample mean came out to be 99.99. So I can say that this is very close to population mean. Standard error is 0.6324. Upper control limit is 101, and lower control limit is 98. Upper control limit means mu, that is that 99.99, this plus 3 multiplied by sigma divided by root n, and lower control limit means that mu 99.99 minus 3 into sigma divided by root n. So that is what you are finding, plus 3 sigma divided by root n, standard error, that is this, and here 3 times standard error minus you are doing, so that is also sigma divided by root n. Okay, and then you plot it. If your plot crosses this upper control limit and lower control limit, will be your, say, boundary. If your plot batching process, now plot means you are actually plotting your entire batching process from first batch to the last batch, from where you will get the details about batches like this. This is the means of those each batch, right? This batch means you have calculated. So you plot those batch means on y-axis, and plot the batch number on x-axis, and plot a graph. So you get this kind of graph, that 0th batch, first batch, and so on up to 50th batch, or maybe 0 to 49th batch, and these are the batch means. So you can see that batch means fluctuate pretty highly, and some batches have 101.5 also, and some batches have 98.4 also. But when I found the mean of all batch means, that is the true mean of my sample, it came out to be 99.99. That is almost 100. And also my batch means, though fluctuated, they remain within upper control limit and lower control limit, which my quality control department had asked me to adhere to. So then in that case I will say that yes, that is I have passed, my manufacturing has passed quality control process. So that is first application of central limit theorem. that ensuring quality control in manufacturing is done by just taking sample of limited number of products. Then data sampling in surveys. This is second application. That suppose there is a survey which estimates the proportion of people in a city who prefer specific brand of coffee. Now, suppose there is a small town, not even a city, whose population is 10,000, and you want to just ask a simple question: do you like Nescafe, or yes or no? Okay. Now, suppose Nestle is only doing that survey, and they have decided that their preference rate should be 0.6. So that means that is their targeted like rate. That out of every 100 persons to whom you ask, at least 6 should say that not 6, 60 should say. 0.6 means 0.60, right? So 60 should say that they like Nescafe, and 40 should say that they don't like Nescafe. Now you do your survey and ensure that whether actually when I ask people that their responses are closer to this preference rate or not. That is what Nestle company has assigned it to you. And similar assignment it will give in each city, small or big. Okay, only this number will keep on changing. Okay. Now here I just have put this a few one or two things for kind of information. One is this thing, that if you take random sample of respondents and compute the proportion P of coffee drinkers who prefer the brand. A proportion means what? You take a sample of say 100 persons, and among them 55 say that they prefer Nestle. So what is the proportion? 55 by 100. Okay. But if 75 says that they prefer the Nestle, then you will say that proportion is 75 by 100 or 0.75, right? Now, once that P is known, that is proportion is known, then the sampling distribution of that P will follow normal distribution for a large sample size if sample size is large and this is the distribution. Now, what is this distribution means? That on x-axis I will put that P, that is that proportion, okay, this P, and on y-axis I will put some variable like P into 1 minus P divided by N, where N is the size of the sample. Then that graph will be normal. That is what statistically is guaranteed by central limit theorem. So I will take sample in that manner, or my proportion is such that it will allow me to adhere to the such normal distribution. Okay, and for that I will select sample in this manner. So my population size is 10,000, that is the total number of citizens in that small town. Preference rate is 0.6. So Nestle company says that if you ask 100 people, then we want that 60 should say that they like Nestle. Otherwise, we will have to take some remedial measures. Now, obviously, 60 should say, and suppose your company is very strict that they don't want lower side also and higher side also. So that means if 58 say, that is fine. But if only 50 say that they prefer Nescafe, then it is alarming. And similarly, if on the higher side 63 or 62 is acceptable, but if 70% say, then either company will tell you to make new sample or maybe do more detailed study, and even if that more detailed study will also confirm that no, 75 is the proportion. This is the population mean which the company is targeting. But if your sample mean comes out to be 0.75, or maybe on the lower side it comes out to be 0.73, sorry, 0.33, or on the higher side 0.80, right? So too high number of people preferring Nescafe, then also Nestle will not accept your survey, because it may feel that you have perhaps lured the respondents into some giving this kind of answer by maybe you will get a free discount coupon or some other thing, or maybe you did not do your sampling process properly. In short, the company wants to limit both higher and lower sample mean with certain confidence interval. So that means two-tailed z-test will be done. Higher also, on the higher side also there will be rejection region, and on lower side also there will be rejection region. Okay, so we have done that in earlier example also. So we are knowing, right? So the diagram I pasted just for that. Okay, forget about this Z statistic. That was Z statistic for that example. So it is not Z statistic for our example, right? But this two-way Z test you want to perform. Now you first generate a population np.random.binomial. Why binomial? Because your question is simple. Do you like Nescafe? Yes or no? So it has only two choices, binary choices, just like head and tail, that kind of example. So binary population, and preference rate is P. So that means you are trying to generate a population whose preference rate is 60% and size is equal to 10,000. Remember that this population you don't have to generate, right? Here we have to generate because we cannot go into a city and ask people. So I have to create a virtual city like that. So I'm creating a virtual city of 10,000 citizens, and this is the population, right? Now I take the random sample. So from here, the work of data scientist will start. That he will take a random sample and the size is 200. So that is fairly large size, because this assumption that this will become normal P, and on one axis and root P into 1 minus P divided by N on other axis, that distribution will be normal provided N is large. Now large is not super large. It is always compared to the population size. So compared to 10,000 in population, 200 is pretty large. So then you can say that sample will be np.random.choice from population, sample size, and take the sample width. Replacement is equal to false. That means don't ask the question to the same person again. And if you have asked the question to one person, then that person is now out of your prospective person whom you will ask the question, right? So you are doing sampling without replacement, okay? And sample size is 200, and from population you select any 200 randomly chosen people. That is what is the meaning of this sentence. And this is the beauty of Python, that it closely resembles English language. If in English language I want to speak this line, then I will say that from my population of 10,000 people, select 200 people, because sample size is 200, right? So select 200 people without replacement, doing random choice, and select, assign those 200 people as my sample. Let us print my population and sample. Population has to 10,000, so that is why it displays only this much. But 1 and 0, so there are total 10,000 such observations are there. And 1 means likes Nescafe, 0 means doesn't like Nescafe. Okay. Now sample is this of 200 observations. There each of the observation is printed. So doesn't like Nescafe, 0, likes Nescafe, 1. These are all who do not like Nescafe, 0, while these are all who like Nescafe, 1, and so on. Right? Now you want to perform two ways that test, because the company has told you. Otherwise, company may simply say that we don't care if more number of people prefer Nescafe, but less should not be there. Then in that case, your this negative region would be the rejection region, but on the positive side, there will not be any rejection region, right? But here company has clearly said that we will not accept your survey if it gives too low answer than 0.6 and too high answer than 0.6 also. So you have to take rejection region on both sides. So sample proportion you are calculating, and that is np dot mean of sample. What is proportion? Proportion is just mean of this value, because these values are 0 and 1. So if I find mean of them, that will give me the proportion only, that what proportion are preferring, 1. Okay, because the rest of the people are not preferring, but they are only zeros. So how to find that proportion, or rather why that proportion is found? Because this is what says that on x-axis proportion and on y-axis under the root p into 1 minus p divided by n square root. If you plot, then that would be normal. So I find proportion p, this is my p. Okay, now I find standard error. What is standard error in my case? It is sigma divided by root n. So that is np dot square root, not here root n, here sigma by root n. Here this itself is the standard error, right? So in that case, it would be sample proportion multiplied by 1 minus sample proportion divided by sample size. Sample proportion itself is p. So p into 1 minus p divided by n, and everything under the root. Is it actually the same as this? Right. Okay. So then you plot a graph of this versus this, then it will be a normal distribution. Now you have to decide what z-score you want to use, and that will depend upon what confidence interval the company has asked to ensure. So suppose the company asks you to ensure 95% confidence interval. Now for 95% confidence interval, that alpha is actually 0.05, right? 0.05. And if it is 0.05, then 1 minus alpha is actually 0.95. That is how 95% confidence interval corresponds to 0.05 alpha. But here we have not taken, though here it is written 95% confidence interval, it looks that we have taken 97.5% confidence interval. Why this 975? No, it is still 95% confidence interval, and it is still alpha is equal to 0.05 only, but we have two tailed tests. So that is why on either side, how much will be the value? Half value. So that is why 0.025, and that means 1 minus alpha will be 0.975, right? So if you create that z-score, then the z-score will be norm.ppf. You imported norm because wherever z-score is to be used, there is no direct z-test which you can obtain from any library. So you have to calculate the z-score for 0.975, correct? And once that is created, then you can find lower confidence interval. So that is equal to p minus z-score multiplied by the standard error, where what is the standard error? That is this. So p multiplied by these two terms in multiplication, this is the standard error. So p and the standard error are multiplied, and then z minus that product, and z plus, p minus that product, p minus z into standard error, and p minus p plus z into standard error. So that means p plus z multiplied by this, that is the higher limit, and p minus z multiplied by this, that is the lower limit, right? So if you do that, then you can find what are the upper and lower limits for the confidence interval. Then you can write confidence interval also. So z-score comes out to be 1.9599 only. That is what I was saying, that it was looking like you are taking 97.5% confidence interval. No, ultimately what you got as the z-score 1.9599, or that is 1.96. So that 1.96 corresponds to what? 95% confidence interval. So it is still 95% confidence interval only, but I explained the reason that because it is two-tailed, you have to take alpha is equal to this much, and therefore here you have to put this value, right? 1 minus alpha value. So what is the formula to calculate that score? Then norm.ppf, where norm you will have to import from here, and norm.ppf into 1 minus alpha, where alpha you are already knowing what confidence interval is you are targeting. So then you can easily calculate that score. When that score is calculated, you can easily find the lower confidence limit of confidence interval and upper limit of confidence interval. And if you find it, then you can get your confidence interval to be 0.53 and 0.66. So you can say that, okay, you can respond to the Nestle that you were targeting a preference rate of 6. And when we did our survey, then we found that, yes, the sample proportion is 0.59. So that means that, yes, 0.59 or 59% of the people prefer the Nescafe brand. So that means you are saying 60% of the people, and we found 59% of the people. And the confidence interval in our finding is 53 to 66%. So that means we are confident that even if you take 100 more samples and find the sample mean or sample proportion in this case for all of them, then in 95 of those 100 extra samples which you will do you will find, you will take the sample proportion will fall in this range only, 0.53 on the lowest side and 0.66 on the highest side, right? So that is the meaning. Now this algorithm performance evaluation. Now that is the third and the last application of central limit theorem. For example, you are doing a machine learning project and you evaluate a machine learning model's performance using k-fold cross-validation. So you want to check that whether by taking that k-fold cross-validation, the performance actually improves or what, okay? And for that, you are taking this kind of example, cross-validation performance matrix. So we simulate model accuracy scores from k-fold cross-validation and summarize them with confidence intervals. What is k-fold cross-validation? For the benefit of those who forgot, I am showing you. Now this is what is that k-fold cross-validation, right? What we do in our model training process is we divide the entire data set into test set and train set. And then we train our model on the trained data set. And then once the model is ready, that trained model is used on the tested data set. But you can make your process more robust by trained data set also. You can split it into many folds like this, okay? So that means among the trained data set, say 1/4. So that means, say trained data set is divided into 4 parts, 1, 2, 3, 4, 5, 6, 5, okay, 5 parts. And among them, one part is used as test. Say the very top part is orange, then that is used as test, and the remaining 4 are blue, so that are used as train. Then in next iteration, the second part is used as test, and the remaining 4, that is 1 above and 3 below, these 3, they are used as test, and so on. So these are called the different folds, and we measure the matrix accuracy or F1 score or whatever matrix we are calculating for this each split, and then finally we find the average of this. Now the question is, why this is done? Then it reduces the overfitting and it makes the model more robust. So the question, the thing is, how do you ensure after doing this k-fold validation, how do you ensure that the accuracy actually increases? Of course, when you are using some library for import grid search CV, and then you directly use it to train your model, then those makers of that grid search CV, they have themselves ensured that by doing this process and by finding average performance, the performance definitely improves compared to taking just one simple plain train and test split, okay? But how do they ensure while designing that grid search CV, or even in fold also, there are many type of folding. This is called k-fold cross validation, then there is stratified k-fold cross validation and all others. So those who developed that technique, how did they ensure that process? Because they have to convince other developers. Python Developer Foundation will not accept their claim just like that. They have to convince the other developers that yes, this process makes the model more robust, reduces overfitting, and increases the accuracy. So this is how they convince. This is a very simplified experiment, but somewhat this kind of experiment they do. Again, NumPy is imported, and from scipy.stats we import norm. Okay, norm means as soon as norm is seen, you should understand that z-score will be used here also. K folds, so you are deciding that 10 fold you will be using. So here there are 5 folds, but instead of that, there will be 1 orange and 9 blue, okay, all over the diagram. So that means 10 fold cross validation you are using, and you are simulating some accuracies which you got. So again, this is the data. So here we are simulating, but there you will actually execute each fold one by one, okay, and you not each fold, sorry, but you will do the 10 folds, and you will create a sample of size 10 k folds, means size 10, and standard deviation some accepted value, so here 2%, and some minimal accuracy you are targeting, that is 85%. And then you will actually conduct the experiment, then find all the accuracies that you will get as a list. So here that accuracies is that list which you are getting experimentally or empirically, but since I don't have the facility to do the experiment here, I am simulating it. Okay, so that is fine. So here, suppose I write one more line, accuracies, and then I can take these on the lower cell. So let us first plot those accuracies. So then you can see these are that tenfold. So during first time when I did this first split, then I got this accuracy. Then next time I did second split, in which first was taken as train, second was taken as test, and last 8 were also taken as test, because this is tenfold, right? So then they were taken as test. I got this accuracy. Then third time I did the third split, and at that time first and second were part of train, third fold was part of test, and the remaining 7 folds, they were also part of train. So that time I got this as the accuracy, and so on. I did up to 10 splits. So here 5 fold is there, so 5 splits. But if 10 folds are there, then you will have to do 10 splits. And I measure the performance or accuracies for each, and I got these values, right? So this is an experimental data. This is given to you. Now you have to check whether the whole business which you have done, because it is computationally intensive business, so whether there is some real benefit of doing this or not. So you find first mean accuracy, mean of all these 10 splits, right? Then there is already a standard error. So find that there is already a standard error, but rather find the standard error from this sample. Okay. So that standard error is sigma, standard deviation of accuracy, sigma with degree of freedom 1, because it is for sample, divided by np dot square root k folds. That is np dot square root number of samples. Here number of samples is equal to number of folds or number of splits. So that means if 10 fold, then 10 splits are done. So here 10 observations will come. If 5 fold, then 5 splits are done. So in that case here 5 accuracies will come. So this n k fold is actually n. So this is our well-known formula only, sigma divided by root n, right? So if you do that, that will give me standard error. From that you can always find the z-score. Here also you want to ensure two-tailed, and therefore though the confidence interval is 95%, you are using norm.tpf as 0.975. Okay, so that is what I have earlier also written, that 95% confidence interval, but that is alpha is equal to 0.025 on either side of two-tailed test. So here and here 0.025 here, 0.025 here, so that is 0.05, that is the alpha for 95% confidence interval, and therefore here 1 minus alpha also you will take for any one side only, so that is 0.975. Find the z-score. You will get z-score is equal to the 1.96 only, that we have already checked in previous example, but for the benefit of those who are attending lectures in random order, so they might be here without attending previous lecture. So then 1.9599, so that is the z is equal to 1.96, okay, and that is for 95% confidence interval. Now here confidence interval lower is equal to the mean accuracy of this 10 splits minus z-score multiplied by standard error, and upper is equal to mean accuracy plus z-score multiplied by standard error. Mean accuracy you have found here, and z-score also you found here now, standard error also you found here now. So then you can use those values, and that will give me what is what were cross-validation accuracy scores. So for each split you got these accuracies, right? 0.8599, 0.8427, and so on, 72 and so on. But for as a whole, what accuracy will be displayed by your algorithm when you use 10-fold cross-validation? It will display not accuracy of any one fold or any one split, but it will display the accuracy 0.86. That is the mean of all 10 splits. And you can see that it is fairly large. 0.86 is larger than most of these accuracies. These two are less. These two are also less. This is also less. So there are 5 which are at least less, and many are almost same as 0.86, right? So mean accuracy is definitely good, and that is within the limit of what you are targeting. You are targeting how much accuracy? Somewhere here, yeah, 0.85 with a standard deviation of 0.022% standard deviation. So you can say that yes, after that 10-fold cross-validation, the sample accuracy would be 0.86, and therefore population accuracy is also 0.86. And we can give that confirmation with a confidence interval, 95% confidence interval, that the accuracy will always be between 0.85 and 0.87. So it will always be more than your lower limit which you are targeting. That is the greatness of that k-fold cross-validation, that either it is this much or it is greater than that, but it will not be lower than that. The mean accuracy will not be lower than that. If you repeat this process 100 times, then in 95 out of 100 times, the mean accuracy will be in this region. Okay. After all this, we can do the definition of inferential statistics. As such, I have spoken that definition many times. But what is inferential statistics? Then this business is inferential statistics. We try to estimate whenever the large population is not possible to study every observation in a population. We try to take independent samples from that population where sample size should be greater than 30. Okay, and the samples should be randomly selected and they should be properly representative of entire population. So that means not that all samples are selected from one region of population and all rest of the regions are simply ignored, but one or two data points from here, one or two from here, one or two from here, one or two from here. That is how you will make that 30 observations or greater than 30, 50 say observations. Then inferential statistic is nothing but measuring various sample statistics like sample mean, sample standard deviation, sample standard error, etc., and ensuring that these sample statistics are accurately attributable to the entire population with a certain confidence interval, sufficiently high confidence interval. Now you read this. Inferential statistic allows us to make predictions and inferences about population based on sample of the data drawn from it. This part of statistic is fundamental in hypothesis testing, where we make certain assumption or hypothesis about a data set and test these assumptions statistically. Okay, so this is where this chapter ends. These are exercise questions, so they will look like very easy questions compared to the lectures which we have done. So thank you, and again thank you for hanging on in this long chapter, and we will meet again in next chapter, chapter 20, first lecture, right? So we wind up this chapter here.